the disturbance from animal birds, and then immediate rain, and then the dust particles accumulation. These three limitations were overcome in this direct solar drying method. But the fourth limitation, that is the color degradations, could not be overcome in this setup, because here also the solar light will be collected by glass plates and then directly passed out on the food products, because here the food products are kept, you can see it's, I think chili is kept inside, red chili is kept inside. So in that case also, the red chili is getting a direct exposure of sunlight. So in this case also, the color degradations will be there. So now for avoiding these limitations in the direct solar drain, people found another method called indirect solar drain. So here, the food products are kept here. You can see this is called the solar air collector. This inclined part is called the solar air collector. And this is called the drying chamber. Inside the drying chamber, the food products are kept. Inside the drying chamber, there are trays. On the trays, the food products are kept. And then here in the solar air collector, there is a inlet. The air will be collected inside, and then the air will be passed through the solar air collector. It is simple rectangular tunnel only. The air will be entered inside and then heated because of the glass plate. And then because the exit air temperature, now let us assume the air temperature will be around 35 degrees Celsius. Fresh air temperature will be 35 degrees Celsius. After heating, the air temperature will be 70 to 80 degrees Celsius. You can imagine. So if the air temperature will be 70 to 80 degrees Celsius, or the air temperature is increased to 70 to 80 degrees Celsius, because of the free energy, we are not making any electrical energy to heat the air, then it is much beneficial to us. That temperature is used to heat the food product, and then the food product is allowed to get the heat, and then the moisture is removed on the food product. So this is the case in the indirect solar drain. So here, the fourth limitation, that the color degradation is avoided in this setup, because here the solar energy will be collected in the solar air collector, and then the food product is kept in the drying chamber. Therefore, the direct exposure of sunlight is avoided in the indirect solar dryer setup. So that's why this setup is used in almost all the places, even in Andhra, Telangana, a number of places. And the people are manufacturing, and then there are certain companies are purchasing, or means fabricating this setup and then selling to farmers. The farmers are using this type of indirect solar drain. Most of the time they are drying ginger, corn, and then chili, even green chili also they are drying. And then like leaves also they are drying. Some medicinal leaves like tulsi, peppermint, like that some leaves are also they are drying. And then the dried products are available in the market. Even if nowadays you can see in all the dried shops, having almost all the dried vegetables, dried fruits, dried leaves, including curry leaves. Packeted dried leaves you can find on that. So it is one of the biggest success in Telangana and Andhra. Maybe other states also it is there. Tamil Nadu also it is there. You can find these dried products, because the products which are dried in the indirect solar drying will be very neat, very fresh, and that can be consumable. If any, even if you pour some water, and then we can consume anytime, whether it's a fruit or vegetable. Yeah, whatever I mentioned, it is here. Yeah, some introduction about this. The solar installation is mentioned here. Yeah, this is the setup what we have developed, the indirect solar dryer. Whatever I explained in this last setup that we already developed here. There is a solar air collector. There is a chamber. And this is the 2D diagram we mentioned here. In the solar air collector, you see it's a inclined plate. In the top, you are keeping the transparent glass cover. That means simple window glass cover is kept inside. In the bottom, insulation is provided, because whatever the heat trapped inside the system should not be lost. That's why we are providing Rockware insulations. And then we are providing a absorber plate here. Absorber plate. That absorber plate, we are providing not a straight plate, not a flat plate, or not a smooth plate. but we are providing with some corrugations. Triangle corrugations are provided here. You can see the reason is once the air will be entering here, if it's a flat plate, then the air will be heated because of the smooth plate. But in the corrugated plate, the heating of air is more because of the reason is more surface area is there. Because of the corrugation is provided, more surface area is provided. Therefore, because the heat transfer is directly proportional to surface area. And then another one is this corrugation always providing some turbulence, air turbulence. So since the air turbulence will be there, this air temperature inside this SAC tunnel, this rectangle tunnel, is almost like a uniform temperature because the air mixing is taken place very perfectly. And if the air perfectly mixed and then will be reaching to the chamber, this is the drying chamber. Inside the drying chamber, we are keeping the trays. If the air is perfectly mixed and then reached to the drying chamber, then the drying will be perfect and then the dried products also will be uniformly dried. So that's why we are providing the corrugated absorber plate. So now we need to solve this problem. How CFD techniques will be helping to solve these problems in the. Okay, so initially, when the product is dried, we are keeping the food products in the tunnel, sorry, in the trays of the drying chamber. When the food products are getting heated and then losing its moisture, it's a simultaneous heat and mass transfer process. Actually, drying is a simultaneous heat and mass transfer process. So during the process, the food is getting heated and then it's losing its moisture. Okay, so that aspect is modeled in CFD. So here we are keeping a single rectangle piece of food product. So let us assume a potato cube. And then we are not taking the lot of potato slabs. We have taken only one potato slab. And then the potato slabs are kept inside a test section. Let us assume this is a wind tunnel test section. And then we are sending the hot air from one end to other end. Okay, so it's almost the same problem is approximated in this way, and then the food product is kept. Here also the food product is getting exposed by supplied air. Here also the food product is supplied by the exposed air. So the air will be entered inside, and then this is a heated air. Let us assume this is 70 degrees Celsius here because in this setup, the outlet temperature is 70 degrees Celsius. So the 70 degrees Celsius is entering inside, and then the food product is getting exposed by the hot air, and then finally the outlet, the hot air is coming outside. So this problem is solved, and then if the problem is solved with the help of continuity equation, momentum equation, and then energy equations, then we can identify how the uh, velocity profile inside or the air profile inside, how the pressure distribution inside, how the temperature distribution inside the tunnel, then we can identify it because this type of analysis will be helping us uh, how the properties of these fluids and then how the product will be getting heated. So that's why this problem is solved in the CFD case. So now based on that, we could able to get the velocity distribution. Sorry, this is temperature distribution inside the tunnel. So the tunnel, this is a tunnel, test section tunnel. Here we are keeping the food products. It's a rectangle object. The air is sent from here, left to right. This temperature condos, yeah, at a different velocity because we varied the inlet velocities also 2 meter per second, 4 meter per second, 6 meter per second. For different velocity conditions, how the temperature profiles look like that we could be able to solve with that here. You can see how the profiles are looking here. When the velocity is 2 meter per second, the temperature profiles are almost like a symmetrical, but slight wavy nature is there. When the air temperature is, sorry, when the air velocity is 4 meter per second, the symmetricity will be slightly varied. But anyway, the profile is almost like a stable profile. When the velocity will be increased to 6 meter per second, then the profile will be almost the 4 and 6 meter per second is almost the same, but the boundary layer developed over the food product is slightly less because of the higher velocity. Now, this is the velocity distribution over the food product. Okay, at 2 meter per second, how the velocity look like? You can see the 2 meter per second is almost like the wavy nature is coming. That means the flow instability is coming and then the air will be moving. When it is 4 and 6 meter per second, the profile is almost like a symmetric profile. You can see on that. And then you can see when the air will be reaching near to the surface, inlet surface. Let us assume this is the inlet surface and then this is outlet surface. When the air will be reaching and then hitting the inlet surface, and then there the velocity will be around 1 meter per second. But when it is just behind the object, you can see the velocity almost 0 meter per second, or sometimes negative velocity. There is a chance now when the air will be flowing over the object, wherever it is hitting hardly, then those places the velocity will be there. There is a place, a wake will be formed just over the object. That's why somewhere the negative velocity is found on that. So these type of studies will be helping us how to the heat transfer will be taking place, how the mass transfer will be taking place from the product. This can be evaluated with the help of CFD simulations. So here there is nothing to explain because 4 and 6 meter per second is always producing uniform temperature profile and then symmetric velocity profile. So now in the part of the CFD simulations, whenever we will be keeping the food product inside a tunnel, it is getting heated and then the moisture is removed. Then one important parameter is involved here. That parameter is called heat transfer coefficient. Convective heat transfer coefficient. You maybe remember on that. It is usually denoted as H. It is watt per meter square Kelvin. So how the heat transfer coefficient will be, or what are the values of this heat transfer coefficient on different surfaces? So that we wanted to know because that is one of the effective parameter which is helping to know how the heat transfer will take place, how the mass transfer will be taken place. So that's why we estimated the both values, heat transfer coefficient as well as mass transfer coefficient value. That is plotted in these plots. You can see this is the food products, and then when the food product is kept here, initially the air will be flowing and then hitting the inlet surface. Then how the heat transfer coefficient values will be on the over the distance of the food product. The distance is 4 into 2 into 2 centimeter. So now I plotted the heat transfer coefficient value with respect to the depth of the food product, 2 centimeter. Okay, the values are on that. At 2 meter per second, the values are from approximately 68 to almost 50 watt per meter square Kelvin. At 4 meter per second, it's almost 70 to 78 watt per meter square Kelvin. At 6 meter per seconds, the values are almost from 80 to 84 watt per meter square Kelvin. So from this analysis, we can get the awareness here on that. When the velocity is increasing, the heat transfer coefficient is always increasing. It is correct only. In the practical also, it is correct. When the air is flowing fast, or if you're putting the fan in the top speed, then the heat transfer coefficient between the human body as well as air will be more. That's why the body will be getting more comfortable. The sweating will be removed quickly. And then heat transfer will be always taken place as well as mass transfer also taken place. So that's why if the velocity is increasing, the heat transfer coefficient is always increasing on the inlet surface. Now the same thing is plotted for the outlet surface. For different velocities, it is plotted. Here also, when the velocity is increasing, the heat transfer coefficient is increasing. But at the same time, if you compare both surface facing inlet and then surface facing outlet of the food product, the values are, you can see the surface facing inlet, the values are ranged from 50 to 84 watt per meter square Kelvin. But in the surface facing outlet, the values are lies between 10 to 45 watt per meter square Kelvin. Okay, so the comparatively the surface facing inlet, the surface facing outlet values are less. Already we have seen the air velocity is almost negative value in the behind the surface of the product. So it is reflecting in this heat transfer coefficient also. Okay, so that's why the values are slightly less compared to the surface facing inlet. Similarly, the heat transfer coefficient on bottom and top surfaces and then front and rear surfaces is plotted. The values are varying in a similar pattern, and then the average values are also almost the same only. So there is nothing to explain here. So these values will be giving some input to us that how the drying takes place, how the heat transfer coefficient will be impacting the uh, drying process or the simultaneous heat and mass transfer process. So like that we can get the information, and that such type of results are very rich for drying processes. So the drying industry is always studying these studying these values, and then accordingly they are identifying how to manufacture the solar dryer, and then they're making the values because these values are necessary for some modeling purpose, mathematical modeling of drying problems. So now this one is heat mass transfer coefficient. Heat transfer coefficient, actually heat transfer coefficient and then mass transfer coefficient almost a parallel parameters. Almost a similar physics is behind on that. How much the heat is transferred. So here it is how much the mass is transferred. Like that. Therefore, the values are different, but the nature is almost the same. Okay, so this profile and then this profile, nature is almost the same, but the values are, these are almost 0.0 to 0.08 mass, meter per second. Yeah, now the mathematical modeling, how it was done, it is mentioned here. So we solved the heat transfer equations because it's a three-dimensional problem. Therefore, we have taken a three-dimensional heat transfer equations and then three-dimensional mass transfer equations. These two equations must be solved simultaneously because this D is a function of temperature. That means let us assume this is equation number 1, this is equation number 2. This D, the D which is situated in equation number 2 is a function of equation number 1. That's why. So whenever we will be solving the second equations, without the help of the first equations, we cannot solve it. Okay, the first equation belongs to heat transfer, second equation belongs to mass transfer. So these two equations must be simultaneously solved. This is heat transfer equation, this is mass transfer equation. That's why it is called the simultaneous heat and mass transfer equations. In practical also, the heat and mass transfer process, example, the drying process cannot be separately explained. We have to explain the heat transfer as well as mass transfer simultaneously. In the mathematical case also, both equations must be solved simultaneously. Then only we can get the temperature and moisture distribution inside the product. Okay, so here, these are the boundary conditions we need to use. You can see there is a value of H here. So this H only we already found and then plotted here. So this H we have estimated, and then by using curve fitting solutions, we incorporated in these equations, and then we have solved these equations and then got the temperature distributions. Similarly, this is the mass transfer boundary conditions. So here we need the help of mass transfer coefficient. The mass transfer coefficient is taken from these plots and then incorporated here in terms of curve fitting equations, and then this mass transfer equation is solved and then moisture distribution is found. So these are the, yeah, here we mentioned 6 equations because since it's a three-dimensional problems, we need to give 6 boundary conditions. That's why these equations came on that. Yeah, I told that D is a function of temperature. D is equal to D naught into exponential of minus 999 by temperature. So if you wanted to solve this D, then it is a function of temperature. Okay, so that's why I told it's a simultaneous heat and mass transfer process. So these are the assumptions we considered. Moisture content independent thermophysical properties, negligible shrinkage or deformation of the material during drying, negligible heat generation inside the moist object, and the negligible radiation effect. We didn't consider the radiation part. Actually, this problem we solved in 2007, 8 times because those days the computers are not very effective to solve these equations. Because this itself is taking almost 7-8 hours, since it's a three-dimensional case, each simulations will take 7-8 hours. But nowadays, very costly computers came. So because of that lack of computers only, we couldn't add the radiation effects. You can add radiation effects also, then the code will be a little complicated. Maybe present days computers can be able to solve it, but it's a little difficulty only, but we can able to solve it. So now I could able to visualize the temperature distributions inside the food product. I told it's a rectangle object is kept in the tunnel. In this case, you remember on that, there is a rectangle object is kept inside. I hope uh, the PPT is perfectly visible and then my voice also audible. Can anyone say that? Can I continue? Okay, yeah. So here we could able to get the temperature distributions, on the food product on different slices, because we have taken one slice, but any slice we can get the temperature distribution, because if you solve the problems in CFD, actually, yeah, this problem is solved by writing a computer code by using Fortran 9D. So those times Fortran, I think Fortran's 83, I think Fortran 83. A computer code was written for both simultaneous heat and mass transfer process. It is almost 3,600 line computer code. And then, anyway, it's not necessarily the code can be written in Fortran. You can write in any software by MATLAB or Python or C++ or whatever it is. In MATLAB, some inbuilt options are there. Some matrix can be directly taken by calling the subroutines. Then you can solve it in the MATLAB also. So here we solve the problems and then we could able to get the temperature distribution for different times. 0.167 hour means 0.167 hour means how much? I think it's 20 minutes or 10 minutes. Yeah, 601 seconds. That means, yes, 10 seconds. Sorry, 10 minutes. This is for 10 minutes. The temperature distribution for 10 minutes. And this is 0.5 hour means 30 hours. Sorry, 30 minutes. 1 hour, 2.5 hours. Like that, these values are taken for velocity at 2 meter per seconds. Air temperature is 68 degrees Celsius. There is a slice at 0.01 meter. That means at the middle of the slice we have used. And then you can find on that for different times, the temperature of the food product is always increasing. Could you notice on that? Here, if you take the left side of the food product, the maximum temperature is 320 Kelvin at 10 minutes. It is increased to 328 Kelvin at 30 minutes. It is increased to 332 Kelvin at 1 hour. It's increased to 333 Kelvin at 2.5 hours. Okay, at the surface facing inlet. But the other edge, the temperature is less only. That's anyway true only because we are sending the air in one side. The other side will not be will not be heated that much. That's why the minimum temperature. Hello, that is the reason. The minimum temperature is around 306 degrees Celsius. But the minimum temperature always increasing for different times. At 10 minutes, it's 306 Kelvin. At,
Rainbow color.
At 30 minutes, it is 322 Kelvin. At 1 hour, it is 330 Kelvin. At 2.5 hour, it is 333 Kelvin. Like that, the temperature is always increasing with the different times. It is natural. Whenever we will be drying the food products, it's a time-consuming process. It is taking its own time. And when the time is increasing, the product temperature is always increasing. So that naturality, we could able to get it through this software, through the programming softwares. And then finally, the results are plotted in the TechPlot software. So this is the place we could able to get the temperature distributions. So this is for velocity 2 meter per seconds. And then similarly, we could able to get the moisture distributions inside the food product. Moisture distributions. Okay. So already I told it's always a heat and mass transfer process. When we are solving the heat transfer equation, we will be getting the temperature distributions. When we solving the moisture transfer equations, we will be getting the moisture distributions. Okay, so let us assume the time is 1.5 hour, that means 1.5 hour. Initially the surface moisture is reduced. You see, the initial moisture content of the food product is 4.88 kg per kg of dry basis. Let us remember 4.8 value. You can see the surface, it's almost 1.4 kg per kg of dry basis because it is taken at after 1.5 hours. At the same time, the inside the food product, the moisture is not removed. You can see. So inside the food product it is 4.5 kg per kg of dry basis. It means that the food product is always dried from the surface, and then the interior moisture content will be diffused towards the surface, and then from the surface again the moisture will be removed. The same thing I explained in the introduction of the drying. Okay, so that aspect also perfectly reflecting in this moisture distribution of the food product. So here you can see the inside moisture content is more, the outside moisture content is less. Okay, when the time is increased to 5 hours, now the inside moisture content is, the maximum moisture content is reduced to 4, the outside it is 1.2. That means still the excess moisture content in the food product is diffused to the surface, and then from the surface again it is removed. Now again the 4 is reduced to 2.6 kg per kg of dry basis at 10 hours. This is 1.5 kg per kg of dry basis at 15 hours. Okay, so it is taking almost 15 hours to dry the food products at 2 meter per second at 60 degrees Celsius. If the conditions will be changed, then we will be getting better answers. We will see if you have the better answers. Yeah, like that I didn't present other data, other temperature distribution, moisture distributions for different velocities, 4 meter per second and 6 meter seconds, and then different temperatures. This is 60 degrees Celsius. We solved 70 degrees Celsius, and then 75 also I think we solved it. I'm not producing all the results. What we wanted to convey is similar way, all the food products can be taken and then the mathematical expressions can be used, and then we could be able to visualize the temperature and then moisture distributions with the help of our basic governing equations. So now this is another one equations we solved. I think it is a green piece. Anywhere I mentioned or no? Green piece. Yeah, maybe it's a green piece. Spherical food products. Green piece means, Pache Patani in Tamil, and then Telugu it is, what is Telugu? I don't know. Green piece. Yeah, green piece is solved, and then here could be able to get the temperature distributions for different uh, times, 0.1 hour, 0.2 hours, 0.25 hours, 0.5 hours, 0.6 hours, and then 0.7 hours. How the temperature is increasing inside the green piece is plotted. Actually it is plotted with the non-dimensional temperature. That's why the values are in terms of 0 point like that. So here also the red part means the surface of the food product, surface of the green piece. It is the surface of the surface temperature of the green piece is more. The blue part is less temperature because it's inside the product. Initially, it will not be heated. So like that, the plot is drawn for different temperatures. Now this is the moisture content distribution inside the green piece. Actually, green piece is not like a perfect sphere, but we assumed it's a perfect sphere and then we solved the spherical equations. We solved the spherical equations. Previously, we have taken Cartesian coordinates. Since it's a rectangle, potato is taken. This green piece is a spherical, almost 95% sphericity is there. That's why we assumed 100% sphericity, and then we modeled as a sphere, and then we could be able to get the temperature distribution inside on that. Okay, so this one already explained what are the different accessories of the solar dryer. Yeah, now we could able to apply the CFD concept in the setup itself, and then how the corrugations will be helping us to improve the heat transfer. Here we have given the triangle corrugations, and then different corrugations are there in the literature, like spherical corrugation, sorry, like wire tape corrugations, rectangle corrugations, like zigzag corrugations, There are number of types of corrugations are there. So that also we are solving one by one by using the CFD techniques, and then almost all the works are published, and then still we are working on that. So here instead of a triangle corrugation, we are providing the square corrugations. Actually, the corrugation whatever we kept here, the same problem is taken and then we are solving here. Actually, here the corrugation is on the bottom side of the solar air collector, but here we are providing the corrugations on the top of the solar air collector. Almost both are same only. We are slightly tilting the device and then we are doing the CFD analysis. 1 minute. I will be checking my battery level. Yes, it is coming down. So 1 minute break I will take. I will connect the computer. And the paper எடுக்கலையா? இது எப்படி 30 மார்க் வந்து எப்படி 30 மார்க் எப்படி தெரியல. பேப்பர் அனாவசிய மாதிரி முடியல 8 மணி தான் முடியும். Okay, yeah. Sorry for the disturbance. Okay, can I continue, sir?
Sir.
Yeah, so here we are providing the corrugations, square corrugations on the top of the plate, and then we are sending the air. The remaining thing is everything is same. We are assuming here 1000 watt per meter square of solar insolation will be reaching to the surface, and then we have taken some entrance section, test section, and then exit section. The air is sent in on inlet, and then air is sent outlet, and then actually, this is the zoomed view of the two consecutive square ribs. The distance between the two square ribs is pitch. The pitch is varied in our case. In what pitch we will be getting the maximum heat transfer. That was estimated through the CFD analysis. And then this height also varied. Pitch height, taken as a small e. So these things we varied, and then we could be able to provide the optimized pitch and then height of the square corrugations. And then from that we could able to make some equations, usually called some equations we have generated in terms of Nusselt number, and those Nusselt numbers are used directly, can be used for in your system, and then we can estimate the heat transfer coefficient or whatever it is. So this is the CFD condor plots, how the velocity profile looks like on over the this each and every square ribs or square corrugations. Okay, when the air is flowing like that, the square corrugations always will be, you can see in the zoomed view is mentioned here. Near the square corrugations, the air fringes are formed. Air fringes are formed, and then because of continuous corrugations, the air will be always getting mixed with each other. Air molecules always will be mixed with each other, and then we will be getting almost a uniform temperature inside the duct because of the turbulence nature. So this is one of the good condor plot we have observed through the CFD simulations. These are the input values. The Reynolds number is 15,000, and then P by E means pitch by height is taken as 7.14. This is for 7.14, and then this is for another pitch. Actually, the pitch and then heights are varied. So like that, we done the analysis through the CFD, and then finally we could able to give the optimized pitch and then optimized height, and then which case we have another one parameter called thermal enhancement parameter, or otherwise called thermohydraulic performance parameters, THPP, and then where the Nusselt number is more. Okay, whenever you will be keeping the corrugations, the friction factor will be more. That must be avoided. Our ultimate aim in this CFD problem is Nusselt number must be more and then friction factor must be reduced. Okay, so we have to balance these two parameters and then we can estimate another parameter called a THPP. And then based on the THPP parameter, we can decide this particular pitch and then this particular E can be preferred for the solar air collector industrial applications. So these already we solved and then we could able to solve a number of corrugations like square corrugations, triangle corrugations, and then another one is now arc shaped corrugation is solved by my scholar nowadays. So this work is still going on that. Some experimental studies are there, but numerically there is no studies. Experimental, we know the limitations because we cannot do much experiments and then we cannot get much data. But in the numerical, we can get enormous amount of data and then we can generate more theories based on the result analysis. That's why the numerical analysis with the help of CFD tools always necessary for the R&D purpose work or your project work. So here we have done another one simulations. This is the solar dryer, means the solar drying chamber, and then this is the solar air collector. We made two models. One is a smooth solar air collector and another one is corrugated solar air collector. If you are providing corrugations, how the temperature profile inside the drying chamber, that type of study was done already. There we could able to find out that if you see these two systems, so in this system, the most of the left side is almost having a lower temperature and then right side is almost higher temperature. When we are providing the corrugations, the mixing is taken place. You see inside there is a mixing is taken place. That's why the corrugation always helping not only inside the solar air collector, inside the solar drying chamber also, the air mixing is taken place. Therefore, the product will be dried uniformly. So this study also we done, but we couldn't go for a publications because there are some problems with the simulations because it is one of the 3D simulations. We need more sophisticated computer to run this type of simulations. Yeah, and another one study we done on that. If the corrugation is a smooth one, smooth means theta is equal to 0 degree. The angle of the corrugations will be 10 degree, 15 degree, 20 degree. These things we studied, but we couldn't find much phenomenal development. But anyway, I mentioned here, maybe it will be useful to you. You can also do similar type of simulations. If you change the angle again, do some better, and then sometimes if you get say a better mixing of the air, then that may good result actually. Yeah, this is the inclination angle. Theta at 20 degree, 10 degree, 10 degree is almost giving some good mixture. 15 degree also it is okay. This also drying chamber temperature distribution inside on that. So now this is the first setup solar dryer. Whatever I explained, we done almost 10 problems in the 10 CFD problems. All the works are already published. So still there is a lot of hope on the solar dryer problems on with the help of CFD. The next work is solar updraft tower. So before going on that, sir, shall we go to the all the topics and then finally the question session can be kept, or in between we can cut, sir?
So we can finish it up, sir. And at the end of the session, we have.
Oh, okay, we will go to on that. Okay, so the next setup is called solar updraft tower. This is also we developed in our laboratory. Laboratory means it's not laboratory, it is the rooftop of a building, it is developed, solar updraft tower. Actually, this setup was developed in France. The name is called Manzanares. The city name is called Manzanares. They developed this plant in around 1985. 1985, and then the chimney height is actually this is the tower or chimney. The chimney head is almost 194 meters. They didn't construct actually. Some portions of the chimney is constructed, and then some portion they taken the help of a real hilltop, because this plant was developed in a hilltop. In the hilltop, there is a natural chimney tower is there, or in a evacuated or not evacuated, like a hole is there in the hill. There is a hole is there, and some places they are occupying by providing some chimney, and then other places it will be natural hill will be there. But in 1985 they developed, and then 1990 the plant was collapsed because of a heavy wind. So now there is no real plants all over the world, but there are some rooftop plants are there, including NIT Warangal. We have developed this SUT plant. Actually, the concept is very simple. There is actually, this is a two-dimensional diagram, but imagine this like a three-dimensional diagram, just like a 360-degree circular solar air collector. Circular solar air collector. This plate is solar air collector. Just imagine just a 360-degree. And then in the center, there is a opening place. In that opening, we are providing the tower. Tower are called chimney. Okay, let us assume this is the ground surface. The bottom line, the black surface line is a ground surface. On the ground, we are keeping the solar panels with some inclination. You see there is an inclination. The solar panels are kept in a circular way. And then you can imagine in between there is a air gap. So the air can enter inside, just like a canopy. This is the plan. This is the real plan we have developed. So this is the air inlet. This is the solar air collectors. And then in the center, we are providing the chimney. Chimney means it's a simple cylindrical tower is provided at the center. What will happen means when the air will be entering inside, solar air collector means it's a normal glass plates only, window glass, whatever we have seen in the solar dryer. A similar glass cover is kept here. The air will be entering inside, and then because of the solar air collector, the work of the solar air collector, it will be collect the solar energy and then it will be transmitted inside the tower. Therefore, the air entered inside the tower will be getting heated. So whenever the air will be getting heated, what will happen? What about the density? The density will decrease. Okay, so let us imagine just as a circular device inside the domain. Let us imagine this is almost like an umbrella shape or a canopy shape. The air will be entered inside. Therefore, the air will be heated because of the solar air collector. When the air is heated, the density will be coming down. Therefore, inside the domain, the density will be low. Outside air, the fresh air, the density is higher. Okay, then what will happen? Outside, fresh air will be there, higher density air will be there. Inside, the lower density air will be there. Therefore, the higher density air always will be trying to occupy the lower density place, lower density region. Okay, so this is the higher density air always entering in the lower density air. Therefore, naturally a draft will be created inside. That draft means the air will be naturally flows inside. Okay, because the heated air will be losing its density, then it's always trying to move up towards the tower. Therefore, the natural vacuum will be created inside, fresh air will be entered inside like that. Okay, so this is a simple concept. When the air will be automatically encouraged inside the tower, we can keep a turbine. We can keep turbine here, or in this 2D diagram, we are keeping the turbine here, one inlet and then one is here. Whatever we developed, the turbine is kept here in this location. Okay, so when the air will be entered inside and then naturally the flow is generated and then the turbine can be run, the turbine can be rotating, and then from that, because the kinetic energy of the working air will be converted into mechanical energy because the fan is rotating now. From that, we can extract the electrical energy by providing the natural provisions. This is the actual work. So this is first time invented in 1945 for some other applications, not for electrical applications. And then 1985, the people developed the plant, but it was collapsed. And at present, we have developed this setup in NIT Warangal. So this is the only one setup all over the world now. So this is the setup we have developed. It is almost the diameter of the this canopy part is almost 2.5 meters. The height of the chimney is 6 meters. It is kept on the rooftop. On the bottom of the this panel, we are keeping some storage material. The energy can be stored if you're keeping proper energy storage material. Here we are using the energy storage material of sand, rock mixes, sand and then gravel mixes. And then top we are keeping a copper absorber plate. Here after the sand we are keeping copper absorber plate. So the copper will be absorbing the solar energy and then will be storing the heat energy with the help of this sand and then gravel. So this is the concept we developed because whenever the sunlight will be there, it will be collected by the glass plates and then it will be transmitted inside, the air will be heated. So the airflow will be always taken place, the turbine always will be rotating, but the system can only run on the daytime only. Okay, so nighttime also we need to run the system. That's why we provided the this thermal energy storage provisions. So the daytime, the air will be heated and then the part of the energy will be stored in the thermal energy storage system. And then after 5 o'clock or when the sunlight is gone, then that time the stored heat energy in this thermal energy storage system will be used to heat the air. And then that heated air always will be, again, the same concept. The density will be reduced, then the natural draft is taken place. So because of the solar energy, the thermal energy storage facility, we could able to run the system round the clock. Even 12 o'clock also we have taken the reading. It is producing proper air velocity. Actually, the velocity noticed inside the system is up to 5.8 meter per second. The maximum velocity is 5.8 meter per second. Actually, if you put the fan with a top speed in our home, then the maximum velocity up to 4 or 4.5 meter per second only. But here, it could able to produce up to 5.8 maximum velocity, and then the average is almost to 2.5 meter per second velocity. It is enough to run the turbine, and then from that we can able to extract the electrical energy. So these are the different components of the setup, and then my scholars are erupting the setup in the rooftop. Pictures are mentioned here. Yeah, some data were mentioned here. So now we could able to see more theories on the solar updraft tower. Yeah, whatever I told is mentioned in this page. We will go for our CFD part. Yeah, one issue is on that. I told the actual height of the chimney is 194 meters, which is already developed in the Mansana's plant. So it is tough to construct such type of chimneys. 194 meters, you can imagine. You can, 100 meters distance running race ground. Okay, so 100 meters, it's almost height 100 meters. 100 meters itself, it is very tough. But if you want to install or develop a 194 meter height chimney is somewhat very tough. That's why commercial investment is higher. But once you installed, this system does not need any much maintenance. So once it is installed, one-time investment only. Then later, the system always generating power, even in the night time also, because of the solar energy storage facility. And then a few prototypes have recently been constructed and projects are being proposed in different parts of Africa, USA, and Australia. But I don't think so. Those studies are not published. I couldn't be able to get any data about the system developed in these countries. Okay, even the low temperature heat is enough. India's solar installation is enough to generate this type of solar updraft towers. Okay, so already yes, one review work is reported in 2016 by Zhu and then Zhu et al. A popular update with the interview of an informed engineering proponent has been published in National Geographic Channel. One video is there in the National Geographic Channel. Already I have seen that one. There are some design factors must be taken care here. The power output depends on primarily on two factors. One is collector area and another one is chimney height. Okay, the collector area is as large as 7 kilometers diameters. So could you imagine 7 kilometers diameters means 7 kilometers diameters. Such a huge circle is needed. So is it possible in cities and then towns? It is not possible. Okay. But we can make even in cities also some secluded places will be there. 1 kilometer diameter solar air collector is planned, but 7 kilometers is not possible. Then we need some rural areas or some desert areas. Those places we can think about this 7 kilometers diameters plant. And then a largest chimney height up to 1 kilometer. Is it possible? 1 kilometer height chimney. Have you noticed anywhere the chimney height is 1 kilometer anywhere? Any industries? I could able to see around 500 meters chimney in Hyderabad. There are some coal power plants are there. Cement factories are there. They are using very big chimneys. Whenever you will be seeing naturally, the height may not be visible, but the real height is almost 500 meters. Okay, such type of construction is needed in this case also. Then we can able to extract more amount of electrical power. The working principle already explained, so here it is mentioned. Anyway, this CO2 is almost zero. We are not burning any fuel. There is no combustion. So there is no carbon dioxide, there is no sulfur dioxide, there is no carbon monoxide, almost zero emissions. Okay, the turbines with a horizontal axis or a single vertical axis turbine can be installed inside the chimney. Okay, and then the water storage, sorry, energy storage, I already explained here. We are providing the natural storage materials like sand and then gravel. Instead of the sand and gravel, you can provide some water tubes also. Water tubes. If the plant is, the solar air collector area is, sorry, diameter is almost 7 kilometers, then we need to lay a lot of water pipes. Then it is sometimes tough to get that much amount of water. Then that plant must be kept near the seashore areas or in the river shore areas. Then we can get frequent amount of water and then the water can be circulated. So such type of one study I noticed on that with water bags or tubes inside on that. And then one study I noticed with the salt water. Salt water means the plant is kept near the seashore and then therefore they are taking the salt water. And then this solar updraft tower also different types of plants are there. So in the first type, it's a convergent type SUT. The chimney is almost like a convergent nature, converged nature. Okay. And then the second setup, it is almost like a divergent nature. Divergent nature. In the third setup is almost like a convergent divergent nature. Okay, so which setup is effective? Then we need CFD techniques to resolve it, and then we can finalize, we can come to the conclusion on that. Let's say the convergent divergent setup is better, or the convergent is better, or divergent is better. Like that, we can come to the conclusion, and then accordingly, we can generate our own plant. Okay, the concept is almost the same because it's almost like the concept of nozzle or diffuser. Okay, the purpose of nozzle is to increase the airflow velocity. Purpose of the nozzle is to increase the airflow velocity. If the airflow velocity will be more, then the air have more amount of kinetic energy. Then the turbine blades can extract more amount of kinetic energy. Therefore, it can produce more. It can produce more speed. Therefore, we can extract more amount of electrical energy. That is the concept we are using here. Different types of plants are used here. Yeah, now we have used CFD techniques. And then we solved the same problems, and then we could be able to get the velocity distributions and then streamline distributions inside the setup. Okay, so this is the velocity distributions, how the velocity air profile will be looking inside, and then how naturally the draft is generated, and then how it is flown through the chimney. Here, these things we could be able to see in the CFD simulations. Okay, the system must be modeled using the modeling software, or even the ANSYS, there is a modeling software, or even you can go with the SolidWorks or CATIA. Again, the modeling can be incorporated in the CFD tool, and then we can run the simulations. In the simulations part, we need to run our normal governing equations like energy, momentum, and then continuity equations, and then we could be able to get the velocity and the temperature distribution inside on that. So here, this is the pressure distribution is mentioned. This is the temperature distribution is mentioned. Like that. So from that we could be able to get on that how the profiles look like, how the flow nature will be inside the setup. Like then we could be able to get a lot of information on that. So this is the plate temperature, observer plate temperature. I told in the previous case, there is a observer plate. Here on the top, there is observer plate. We could be able to get that temperature distribution on the observer plate. If you are providing heat energy storage materials, without heat storage material, and then with the heat energy storage material, with the thermal energy storage material. Okay, if you are providing without thermal energy storage material, the temperature is almost lower. It is around 315, or maximum is 344 Kelvin. Sorry, maximum is 344 Kelvin. But whenever we will be keeping with the thermal energy storage material, the temperature is reduced. The maximum temperature is around 327 Kelvin only. The reason is, if you are providing thermal energy storage system, then whatever the heat will be absorbed by the observer plate will be convected to the thermal energy storage systems. That's why the temperature will be reduced. Maximum temperature is reduced in the thermal energy storage system. So this study also we already done with the help of the CFD tool. This is effect of TS system on 1 centimeter above the observer plate. This is the air temperature, not the observer plate temperature. How the air temperature looks like. So how the air temperature looks like on the just 1 centimeter above the observer plate. So that we could able to get on that. So here also the air temperature is more. The maximum air temperature is more. That is almost 340 Kelvin at the center of the domain. Without the TS system, but with the TS system, the temperature is 318 Kelvin only. Okay, the reason is same thing only, because if you're keeping thermal energy storage system, the copper plate is absorbing the heat, and then it is transmitting, it is conducting the heat inside the thermal energy storage system. That's why the air temperature will be somewhat less in the with the TS system. Okay, so here we studied the velocity, air velocity inside the system without TS system and then with TS system. The first one is without TS system, and then this is the with TS system. The maximum velocity obtained is almost 6.5 meter per second when we are considering without TS system. Okay. When we are using the TS system, the maximum velocity is slightly reduced. It is around 5.2 meter per second. But at the same time, if you are providing the TS system, the system can be run even after sunshine hours also. Even after 5 o'clock, we can run the system. Okay, even night 12 o'clock or even beyond that also, the system can be run. But if you, without TS system, we cannot run the system. Okay, that is the only disadvantages with the first system. Advantages of the second system can be run for round the clock. So now the minimum and the maximum and the average velocity is mentioned for different chimney heights. At chimney height is 0. That means at the base of the chimney, the maximum velocity is around 5.5 meter per second. Sorry, minimum value is 5.5 and then maximum is around 6.7. Average is 6.2 meter per second without TS. At the same time with the TS, the maximum average is only 3.9 meter per second only. Okay. And then when the height is increased, at the height of 2 meter, the average velocity is 5.8 meter per second at the without TS, and then it is reduced to 3.7 meter per second with the TS system. When the chimney height is 4 meter, it is 5.8 meter per second. There is not much difference is there, and then average also 3.7 meter per second. There is not much variation is there. So now the influence of the chimney height. Actually, in our system, we developed up to 6 meters only. If the height is increased beyond on that, how the air velocity will be increasing? So three different locations at the inlet of the chimney base, and then inlet of the system, chimney base, and then outlet of the chimney. Like the three locations, we estimated the air velocity for different heights. So you can see when the height is increasing, the air velocity is always increasing. You see, in this case, it means on that if the height of the chimney is increased to 10 meter, 20 meter, 30 meter, 50 meter, 100 meters, 200 meters, we'll be getting an enormous amount of air velocity. That is the conclusion here we could able to get on that. And then the collector roof angle. Okay, so here the collector, there is angle here. This angle we adjusted for different simulations. It run for 10, 20 degree, and then 25 degree, 30 degree, 35 degree, like that we done different cases. There is not much variations in the maximum air velocity. So it shows that actually this angle we have chosen based on the Warangal's latitude and the longitude. If you wanted to run the simulations for your city's latitude and longitude, and then slightly the angle may give some impact. But we couldn't get much impact. So based on that, if the 30 degrees giving maximum value, maximum air velocity, then we can consider the 30-degree angle, collector angle. The effect of observer plate diameter on velocity on air. Actually, the diameter whatever we have chosen is 2.5 meter. But if the diameter is increased from 3 to 12 meters, 2 to 12 meters, you can see the air velocity is always increasing. Okay, therefore, that's why in the theory they told that there are two important parameters are there. One is diameter of the collector and another one is height of the chimney. Yeah, now I could able to estimate the volume flow rate, velocity, theoretical power output, actual power output, overall efficiency, and then chimney efficiency for different chimney heights. When the chimney height is increasing, the theoretical power output always increasing, actual power also always increasing, overall efficiency always increasing, chimney efficiency always increasing. Okay, it shows that if you take a good height, then we can able to get a very good overall efficiency on that. Anyway, these heights could able to produce very small power output only. The maximum is 3.3573 watt theoretical power. Actually is 0.238 watt only. If the height is increased, we can get a good. We can do the simulations for those things also. We can estimate the overall efficiency. Yeah, this is the case. We estimated I think this is the temperature profile for different inclination of the chimney. So this is a straight chimney. The angle of divergence will be increased. Or maybe the title is disturbing me. Yes. 1 degree, 2 degree, 3 degree, 4 degree, and then 5 degree. If the angle will be increased, then how the this is only domains. We are not solving the equations. The domains are generated for different angles. And then we could able to get the velocity distribution here. When the angle will be 1 degree, the profile will be almost good, and then almost we are getting a fully developed profile. When it is angle is 2 degree, also it is almost okay, 3 degree, 4 degree. But when the angle between 4 degree and 5 degree, the profile, the air velocity is not able to reach at the top of the chimney. There is always some instability is noticed on the air velocity. Therefore, 4 degree, 5 degree may not be fit. Then we can choose anyone, 1, 2, or 3 degree, and then we can choose the chimney angle. For different chimney angle, how the actual power, theoretical power, and then overall efficiency is varied. Like that, we run the simulations, and then we have got on that 4 degree somewhat better for the better theoretical power. It is producing almost 1.35 watt at 4 degree at 600 watt per meter square. If the solar insolation is increasing, then this value is also increasing, but still 4 degree angle is better. If the angle is increased to 5 degree, then the value is started to decrease. Okay, it means that further increase of angle will not help us. 1 minute. So the time is 7:30 or up to 8 o'clock? Hello? Can anyone say the time is up to 7:30 or 8 o'clock?
Sir, up
7:30,
to
sir.
7:30, sir.
Okay. Okay, then I will go to quickly then. Yeah, here we could able to get the temperature distribution inside on that for different solar flex, 600 watt per meter square, 750 watt per meter square, and the 900 watt per meter square. How the temperature control on the observer plate is looked on that. The overall system efficiency is always increasing when the ambient temperature is increasing. Ambient temperature, we no need to go up to 320 degrees Celsius because ambient temperature in some Arab countries, the temperature is more, up to 55 degrees Celsius or 58 degrees Celsius will go. In India, maximum up to 45 or 47 will be there, but still we done the analysis. It may help for other countries. And then the actual power output is estimated for different temperatures. And then we found on that when the temperature is increasing, actual power output also increasing on that. And then overall efficiency also increasing on that. And the next one is solar vortex engine. Actually, the limitations in the solar updraft tower is we need to make a very high chimney. But in the solar vortex engine, similar type of solar air collector is provided here. But here there is a solar vortex machine is generated. Okay, the air will be, you can see this is the cross section of the solar vortex engine. Whatever the air is heated through the solar air collector will be entered through the this solar vortex generator. There is some provisions are there air for air flowing. So the air will be moving through the blades. It's some fixed blades are there. Air will be moving through the blades, and then always there is a turbulence is created inside, and then they will be flowing through a top hole. There is a top hole here. In this picture, there is a top hole here. Then the airflow will be entering. Then if you are providing a boundary here, boundary panel, and then inside the boundary panel, we are keeping the turbine, and then the turbine can be rotated. So in the solar vortex engine, there is no need of to make the tall chimney. Yeah, this is the diagram we have made on that. This is the solar air collector plate. This is the solar vortex plate. This solar vortex plate is zoomed in this way. The air will be ended through the slots. These are the air slots with the fixed blades. The air will be ended inside, and then there is a natural tornado. It is called a tornado. A natural air tornado will be generated, and then the air tornado will be passed through the top hole, and then it will be moving like moving through the external bounding structure called EBS. So here, if you keep the turbine in this place, if you keep the turbine here, then the turbine can capture maximum quantum of kinetic energy, and then the turbine can be run. So this is the concept we developed in the solar vortex engine. Actually, still it is in the developing stage. We are not developing a real setup, but we run the simulations. Yeah, this is the concept. This concept was developed a very long time back. Actually, it was developed, the prototype developed by my card team. They developed a prototype one and then developed a prototype two. And then in the prototype, they have used the agarbatti smoke. And then the smoke is coming towards the top hole like that. So we run the CFD simulations, and then we could able to get this type of air profile from the top plate. So we also could confirm on that whatever we the MyCard developed, the concept is fit for the real setup. Through the CFD simulation, we could able to get on that. So these are the simulations we could able to run, and then we could able to get the velocity profile like that. Yeah, based on that, we could be able to provide different simulations. Yeah, these are the air velocity natures for different slots, different air entry slots. In the circular plate, if you provide 6 slots, then how the velocity looks like, 8 slots, 10 slots, 12 slots, like that we could be able to run different simulations. And then finally, we could be able to come to the conclusion on that. The theoretical power developed is higher in the 8 slots. 3.45 watt power could be able to generated. At the 12 slots, it is reduced to 3.28. It shows that more slot is not necessary. So like that, the problems can be extended in any way by using the CFD techniques. So these are the tools usually we are using: ANSYS ISM CFD, fastest 3D, ANSYS Fluent, TechPlot 360, Minitab 16, DataFit 19, and then recently we are using COMSOL also. And then these are the programming tools: Fortran, MATLAB, Python, C++ also we are using. So that's all. So any questions you please raise and then we will answer now. Sir, is it okay?
Sir, it is okay, sir.
It is okay, yeah.
Okay. So, dear participant, now you can ask any questions related to the particular presentation.
Any questions?
Good evening, sir.
Yeah, good evening, sir.
This is Palani from Tamil Nadu, Dirajilal Gandhi College of Technology.
Okay. Which place, sir?
Okay, sir. Yeah, your presentation is very good and the concept is very, what is that, impressive.
Okay, sir.
Is it possible to commercialize this for making energy?
Yes, that's why. That's why I told you, no, if you could able to solve with CFD tools with the
Okay.
very high chimneys, SUT plants
Okay.
with the 200 meters, then
Okay.
if you get the, definitely you will be getting good results, because the present analysis whatever we done is getting good result. Okay. So if you are making with a 200 meters chimney in the CFD problems, then we can solve it, and then based on the results, you can approach the commercialized energy agents or government sectors or any other sectors. Then sometimes it is possible. We can somebody ready to provide the funding, and then we can generate such a big plant in very secluded place or desert areas or in the rural areas. Definitely there is a chance.
Okay, sir.
Yeah.
Thank you, sir.
Okay, sir. Yeah.
Any other questions from the participant side?
Yeah, if any more questions are there, you can later you can mail me. My mail ID is mentioned here. We have lot of publications. You can get it from a Google Scholar and or my institute website. You can study it, and then if you have any doubt or if you in future if you wanted to work on that, please approach me in mail or through mobile phone. Yeah, is it okay, sir?
Sir, okay, sir.
Yeah.
So it is, thank you very much, Dr. VP Sandarmohan, sir. So really, it is a very nice and wonderful presentation. So I think all the participants really enjoyed the session very much, because as a coordinator of the program, we also learned a lot from this presentation, especially the solar updraft tower. It is a new concept in India. It's the first time you are introducing the NIT Warangal, sir. Really, it is a great thing. Your presentation and the new concept you're starting from. What is the demand of solar? It is the from India. What is the level and all? What is the need of solar energy? So what are the research required? It's a lot of scope for this particular solar technology, solar drying technologies. It is really this researcher who are all involved, particularly solar research area. It is giving some insight to do the research in particular area. So from the coordinator side, really thank you for your nice presentation, sir. So future also we will give a lot of this type of session from in our college, in our university also, sir.
Okay, sir. Yeah, welcome, sir.
So thank you, sir. For a nice, wonderful presentation, sir.
Okay,
Thank
sir.
you,
Yeah.
sir. Good night, sir.
Thank you, sir. Thank you. Good night, sir. I will cut the call.
Okay, sir.
Okay, sir.
Dear
Thank you.
participant, after 3 minutes, again the session will start.
Dear participants, the feedback form is available in the chat box for the session 3. Kindly fill it. My dear participants, I once again repeat it. The feedback form is available in the chat box. Kindly fill it for session 3. Our next speaker, Mr. Praveen, has joined with us. I request the participants to take 2 minutes break, then we'll start the next session. Your kind cooperation, your kind cooperation is highly appreciated in this regard. Please. Praveen Kumar sir, good evening.
Hi, Manoj.
Sorry for the delay. Since our
No,
previous.
no, it is for me it is morning. If you guys can able to see from my back, it's already sun is out. So it is 7:10 here. I am very pleasure to meet you all. Very good evening. I know you guys are already tired by the previous sessions, and it is a long day for all of you. I definitely thank you for all
Thank you
of
for the
you.
understanding. Yeah, thank you. I hope participants are having some break now. Shall we start after 2 minutes?
No worries, no worries. Manoj, yeah, sure, we can do that.
Yeah, thank you, Praveen.
Yeah.
Dear all, welcome you back. Mr. Praveen, can we start?
Yes, I'm ready, Manoj. Yeah, if you are all good, we can start for sure.
Yeah. Thank you, Praveen. Hope the participants have come back. I once again welcome you all to the gathering. Now I request Dr. G. Kalyani, Controller of Examination of Adisangara DBTB University, to introduce the chief guest to the gathering. Ma'am, please, ma'am.
Thank you. I'm very much pleased to introduce our esteemed guest, Praveen Kumar Pugilendi, who is a seasoned expert in CAD, PLM, and systems engineering with more than 18 years of experience across automotive and aerospace domains. He currently leads digital product development initiatives in electrical vehicle space, driving innovation through data-centric approaches using platforms like 3D Experience. His focus areas include sustainable product architecture, engineering change management, system integration, and traceability across the product lifecycle. He is more passionate about enabling cleaner mobility and combining technology and system thinking to engineer sustainable and future-ready EVs. Mr. Praveen Kumar is presently working as a senior manager, product configurations and advanced solution, Lucid Motors. Now, I would like to invite our guest to take over the session. Thank you, sir.
Thank you, Kalyani, for warm welcome. It's definitely a pleasure to meet you all, and I would like thank you, Dr. Manoj, for this wonderful opportunity. He's very good friend of mine during my college days, and thank you, Manoj, for this. Okay, for sure. Before jumping into this session, I would like to ask you, how many of you know what is Lucid Motor or heard Lucid Motors? Maybe you can give thumbs up, or in the chat bot you can put your comments, please. Do you guys know what Lucid Motors? Anytime you heard Lucid Motors in the past? No worries. So I would like to take my journey along with the Lucid Motors, how we achieved the sustainability, or still achieving. It's not sustainability, is not any end. Okay, sustainability along with systems thinking and using system engineering methodology. Okay, so again, good evening, everyone. I'm very excited to be here with all of you for this faculty development program. Thank you for joining today's session on this topic. So today we will explore two big ideas. Yes.
Sorry for interfering you. Yeah, message from our participants that they want to see you clearly. So the backlight behind you is interfering them. That's a request from them.
It's better now?
Yeah. Thank you, Praveen.
No worries. Sorry. Because it's sun here in my back, so probably the reflection.
Yeah, understood. You are in the morning time, the sun is rising. Yeah.
Yeah. Sure.
Thank you.
Sorry for the chaos. Okay,
thank you. Please go ahead, Praveen.
Okay.
Please. Thank you.
So today as I said, today we'll explore two big ideas. One is sustainability in engineering, which is not just a buzzword, but how it really plays out in the practice. We are going to talk throughout this session, and also system thinking, which is a way of looking at the big picture so we can solve the complex problems like building a EVs or without getting lost anywhere. Okay. So definitely, I promise you at the end of the session, if you guys already not aware about what is systems thinking or model-based systems engineering, I will keep it very simple and very practical, and what we gone through in Lucid Motors as our journey. So it's mainly on sharing session rather than kind of I'm giving some research paper or something like that, because I'm more on tools and process and methods area. So I'm just sharing my experience with all of you about our journey. Okay. So now we talk about engineering and sustainability, correct? It is easy to think only in terms of components. If you take a EV, So we have like batteries or motors or softwares. But at the heart of engineering is about creating the customer experience. Our fundamental goal as a Lucid Motors is how we can able to provide the exceptional experience to the customer. Okay, I'll give one analogy. Think about it. Okay, why people will buy the electric car? Anyone is aware? It is not just for zero emissions, correct? It also, especially in Bay Area or US, it is especially because they want to have the kind of exciting driving experience. It is not just giving something to the planet or whatever environmental constraints and all those things. At the same time, we have to give the the experience which they expect, correct? So the way today, if you see the IC engines, they give very kind of thrilled driving experience. There is a good amount of space, just compromising nothing. So that is our Lucid tagline. We will never compromise anything. At the same time, we have to provide the exceptional experience to the customer. So that is one of the key for Lucid Motors. Okay. So I would like to play a small video about. So before that, I will kind of give some sort of context. What is Lucid Motors and who we are? So I'll play a small video for all of you. If Manoj, let me know you can able to hear the sound because that very much matters for us. Okay.
Yeah.
It's pink EV right now. It's pink.
You can able to hear the sound?
Yeah, we can able to hear, but the volume is
Yeah.
very low.
Okay, let me increase it.
Pink right now. This is as good as
And
it
now it's
gets.
fine.
This is one of the best sedans ever made. I'm not saying electric, it's one of the best sedans ever made.
I'd say it's one of the best driving cars I've ever had the pleasure of driving.
Now volume is not there.
You can able to. You are not able to hear the volume now.
Yeah. Now the volume we cannot able to get. So are you working on the volume?
I think probably that might be the issue with the internet, Manoj. Probably you couldn't able to hear much volume.
Okay.
So it
That's
is on and off, or how it is?
It's okay. The
It's
volume is
fine
not.
anyway.
Yeah.
It's more on the background music. It's fine. So I will explain it, or maybe in the next coming slides, definitely we are going to explain our journey and what we have done and what we are going to do in the future. Also, okay, no worries.
Yeah, thank you. Yeah, please go ahead.
Okay, so this is our key milestones, or I used to call it we used to call as a journey. Am I going too fast, Manoj, or it's okay? Or
It's
maybe I
okay,
need to
sir.
slow down. Okay, no worries. Okay, so every innovation, it's as a story timeline. As a Lucid Motors, we started in 2016, and we have started laying down our manufacturing facility, which we used to call as an advanced manufacturing plant. One in Arizona in 2017, and we have launched our first flagship product, Lucid Air, in 2021. The same time, we listed our company in NASDAQ. And in 2023, again, we started producing our product in our AMP2, which is in Saudi Arabia. And today, as we speak, our first SUV is out in the market, which is kind of sold across globe, primarily in US as well as Asian market. I mean, I would say it's on Middle East. Okay, so this is our journey timeline. So what exactly here is we will go deeper into how we approach these kind of challenges, and starting this technology is setting for us, because it is a brand new company. We started around 2016, and as we grow, the complexity also it is growing in terms of data management, in terms of design, in terms of a whole product development. Correct? There are a lot of complexity from a small team into a bigger. Today we have close to 5,000 employees, and we are working in 3 production products, as well as there are future products also it's coming. So the complexity is enormous. So next one is I would like to talk about the core technologies that drives sustainability in electric vehicles. Specifically, when people think EV, first things that usually comes into the mind is battery. Of course, the battery technology is central part of the EV, but it's not only the factor, correct? We need to have a good aerodynamics as a smooth, the car cuts through the air. And of course, the battery innovation, we need to have the energy dense battery. And of course, we need to meet the charging efficiency. And the next one is charging systems, because we need to have a fast charging, which needs to be accessible to everyone, every one of our customers. So why do this matters specifically for sustainability point of view is because every small efficiency here compounds the huge lifetime savings with respect to sustainability, correct? For example, if I can talk about the aerodynamics, which may look in the design choice, but the simple fact is the improving the vehicle drag coefficient by 0.01% definitely adds 5 to 10 miles of range in the vehicle, which means with the less battery, with the less energy, the vehicle drives a little bit longer. So that is a way, kind of sustainability equals with respect to this kind of technology. So that's why always when we say blazing the trail, that term here is, it is not just marketing, it means the leading the way. We are rethinking the entire fundamentals as a system as a whole. So that is the point over here, okay? So one of the key reasons we have been able to lead the EV technology in Lucid, because we make most of our critical systems in-house. So nothing will buy from any of our external vendors like China or whatever the other OEMs will do, because everything is in-house technology. I will highlight few of the things. One of the things is the battery pack, which is very lightweight and it is thermally managed, because the heat control is very, very important with respect to battery pack. And of course, the next one is the inverter, which is the brain that converts the battery DC to motor AC with the incredible efficiency. And of course, we have a motor, which is world's smallest motor in the EV segment. Comparability, if you can name it, it can be a Tesla or whatever the EV is out today in the market. Ours is a compact motor, which definitely, kind of produce the maximum energy per kilogram. So that is one of the key technology which we have in-house. That technology is already recognized by external OEMs as well. They're ready to work with us in that sense. And of course, the software part, people will talk about the software, it's just for the infotainment, correct? But it is not. The software is another nerve system for our entire technology in terms of controlling the energy flow or thermal management, even sometimes the driving experience, because the chassis teams needs to do a lot with the software today. As we speak today in Lucid, most of our vehicle dynamics, it's controlled through the software. And last but not least is our Wonder Box, which is kind of bi-directional charging system that supports fast charging. The same times we can supply the power from vehicle to grid capabilities. So these are our kind of flagship in-house technologies, which as leading help us to lead in this space. So of course, kind of these are the key critical awards which Lucid got. Definitely, kind of the external recognition also it matters, correct? For us, our car owns numerous awards like with respect to efficiency, design, and performance. These are all done by the legit independent reviewers. So definitely, kind of we have one of the best product. So the key takeaway here is, with respect to our subject, system thinking and sustainability is not just as a buzzword. That's what I earlier said. They translate into the measurable recognition. So these are the things specifically, kind of proves we are in the right track. I quickly talk about Lucid first before jumping to the subject. Bear with me. It is not just a marketing. It is, you need to understand what we do. Then we can, I talk about the concept or whatever the, system thinking or model-based systems engineering definitely how helped to shape this entire product line. So that is the main point over here. Okay. So let's talk about our product lineup. So we have started with the Lucid Air, which is a luxury sedan focused on long range. And now after that, we just shifted our gear to the Sapphire model, which is a performance variant, and to the customers who loves the speed and acceleration. And now we are in the Gravity, which is our flagship SUV that balances both range and performance as well as versatility. Okay, each of this product targets different customer needs, but the catch is here is if you do more variants, definitely we have to do more complexity. That's the key here. Okay. Maybe I'll give one analogy. Think about it. A sedan is aerodynamically easier because than SUV, but the SUV is very much challenged in terms of more space we need to provide the same time, which increases the weight of the vehicle, and definitely there are a lot of features. So that ripples through the aerodynamics, or battery requirements, or software tuning, and thermal management. So we have to balance all these things. Okay. So definitely the system thinking is only what allows us to manage all of this. Without that, definitely, kind of you need to design each vehicle almost from the scratch. So it will lead to duplicate effort and increasing error. So the key takeaway here is system thinking is definitely a key for this kind of complexity and versatility. So that is the message here. Okay. So okay. So till the marketing is over, coming to the actual business. Okay. What is the problem? Every new feature, whether it's a battery variant or software mode or supplier component, adds layers of interaction. Correct? Alone, all of these, each one make a lot of sense, but if you put together, it becomes overwhelming for our product. Okay. The key issue here is the traditional engineering methods looks components is in isolation, like mechanical focus on the parts, electrical focus on the circuits, software focusing mainly on the code. But the real world, these kind of silos, different silos, does not work in practical way. Correct? So that's why the system thinking is not optional for any more, especially for EV industry. It is the only way to manage this complexity and ensures the sustainability. Okay, exactly the same thing I'm going to cover on the next kind of slide, which is about automotive trends. Correct? Just bear with me. I have. Okay, so I want to talk about okay, let's zoom out and look what is happening around us. Correct? Mobility itself is going through lot of revolution. Correct? Sometimes it is something which we used to call as a re-evolution. Correct? Why? Because it is not just making cars anymore. We are redefining the way that mobility is going towards the future. How the people move, how they connect, and how the consumes the mobility, correct? Traditional, in our older days, we just buy a car and we kind of after that it is just it's maintained regular maintenance, correct? But today the mobility, it is something like ecosystem, especially in Bay Area or Texas or so much. You might have heard the news, correct? Already we have this Waymo, and Google as it's Google's one is a Waymo, and Amazon as a Zoox, and Tesla as a robotaxi. Even we do have our next ride sharing program along with Uber. So it's more on subscription models and connected service and over the air updates. And also it's all needs to be integrated with the cities, correct? Each city has its own regulation, so everything needs to work together. So the mobility comes today, especially on the EV space. It's not about evolution, it is really a revolution for us. Okay, what that means, the value is no longer just a hardware product, just not a car, correct? So we need to think about the data and the connectivity and the services. Just it is supports those entire ride sharing ecosystem. So in that case, definitely customer will not just only ask while buying these EV cars. So definitely we need to kind of think about how this particular machine integrates with their lifestyle, and how they can able to updates like mobile today. If you buy, but every keep on, there are a lot of updates, how easily they can able to get those updates, and how this is more sustainable in long run in a practical way. So all those entire things, while designing the EV, we have to think and keep it in our mind, correct? So what is the key problem from traditional versus the systems thinking? Let's be honest, correct here. Most of the traditional organization, especially in the engineering world, it is the data are structured in silos. So mechanical engineer is only work in one department, and electrical, it's like our college, correct? Mechanical engineering and electrical engineering and software and definitely the manufacturing. So everything is in the silos, but each of this group actually optimize their own piece of puzzle. But if you take mechanical, they are mostly focused on their weight and design optimization, etc., etc. Electrical, and everyone's they're working silos. The main problem here is when it integrates together, that's where the complexity starts. So there is together it may not work in perfect world. So what we say is in our CEO always says, when we work, it's definitely it's a local win, but it is a global failure. So that's what our CEO always encourage us to do more on system thinking, work in collaboration, and do these systems, model-based system engineering rather than the file-based. So that is the main concept here. Okay. So for example, I give you example which practically we had. Okay. So one of our motor team started changing the winding for the great performance. But what happened, that particular change is drastically increase the heat load. Then because they worked in silos, that is not well informed to our thermal team. So they have done in certain calculation, but because of that, the battery got overheating. So again, now battery teams came into the picture, they have to solve that same puzzle. So in top of that, the software is trying to control the heat, the overall performance of the vehicle, it's getting dropped. So suddenly the actual local win, it becomes a global failure as a system, as a whole, as a car. So that's what kind of the real problem in any of the traditional automotive. And at least as a EV startup, we have that opportunity to correct fast because we are started with scratch, and we are producing the brand new idea in terms of electrical vehicle and sustainability. And we know this puzzle very early, so we are trying to work in the system thinking approach, which helps us to lot to handle this kind of complexity. Okay. So what is the kind of main kind of cost or we have to pay off if we are not handled these specific things in a proper way is cost of correction. In the engineering, there is a golden rule, correct? The later you find the problem, the more expensive is to fix. So if you catch a design flaw in the concept stage, for example, if I'm starting a brand new concept design, so at that time, if I find any problems, it is just a discussion, so it's easy to correct. There is no cost. But at the same time, the same bug, if it is identified, my design is frozen, so it's went to the prototype build or for all the validation side. So definitely it is a little bit more cost because already I brought the hardware and I sent the cost. I released my purchase order to the supplier to cut the tool, which is a huge amount. So all those things definitely to correct, I have to spend more for the new design, new tool, and etc. and the prototype. But if the same thing which we find later in the game in the production, definitely it is a disaster because it is already the vehicle is the customer end, so if find the problem we lose our reputation, and sometimes it will kind of create the brand damage as well. So it is like catching the typo, correct? So if I'm typing something, if something went wrong, if I can able to easily correct it as soon as I noticed it in very early. But if you started printing with the same typo as 10,000 books, of course, everything needs to be scrapped. The similar way in our product development, if you catch in the production, all the inventory, all the money which we spend, everything needs to be thrown away, and we have to spend more in order to correct those mistakes, and which we have to pay a lot of money. Okay, so that is the kind of cost of correction. If you find or if you are not having the system thinking approach in very early, you have to pay. Okay, so what is system thinking? Let's go with the basics, correct? The system thinking is about seeing as a whole. It is not just a part. Okay, instead of asking does my component work? Normally, in our entire company, we ask how this particular component interacts with other component, like how this battery interacts with the motor, how this motor and battery together is controlled by the software. So we have to think as a whole. So it is pretty much kind of it's a mindset shift, because most of our engineers comes from the traditional automotive. They have worked in very silos because it's a big company. There is a lot of teams, individual. They will focus on their own lens. But as a startup and small organization, we are building our company from the ground up. So everyone needs to do everything. Everyone needs to understand everything, each other's elements, so we can able to work as a team, as well as in a collaborative manner. The main key here is the system thinking approach is changes that mindset from working in silos to a collaborative way. Okay, so whatever the system thinking, it is not just any tool or something. It is not just a process, also it is a mindset. So when you adapt it, definitely kind of you really discover a lot of unknowns very early, and you understand the power of integration. So that's the main key. So this is very difficult earlier for us, because everyone comes into the different background and different mindset to bring everything together. There are a lot of investment we have to spend on the OCMs. OCM is nothing but organizational change management mindset. So that is a key. Okay. Because currently I'm leading this MBSc in Lucid, I know very well how much struggle which I faced and still I'm facing in order to achieve these entire systems engineering concepts into the reality. I can definitely kind of I'm privileged to talk about and share my experience with all of you guys again. Okay, now let's connect this mindset into a practice, correct? Like a model-based systems engineering or MBSc. So everyone talks about the MBSc. Some people MBSc means is just managing the requirements. It is not. It is MBSE is a practice which will enhance the systems thinking and model-based engineering and sustainability into a reality. So this is the very key, and this is a practical kind of deliverable for systems thinking approach. Okay. If you talk about the traditional way, the system engineering was mostly on the document based. The requirements created in the words and drawings are kind of in the CAD, the entire design documents in the CAD, all the test plans in the Excels, and entire collaboration happens through emails. That's what, when we started our company, our first product Air, we had the same concept. So all the requirements in different silos. So each of the systems engineering, they're creating their own requirements and keeping it on their preferred tools. Probably in the Word document, something in the Confluence, something in the share file, etc., etc. And based on that, our engineering team designs the product. So there are disconnects. Sometimes the requirement changes, the design team is not properly communicated or aware about those requirements, or vice versa. There are some designs pushes the requirements which connects to the some other need. For example, as I mentioned, traditional, the battery changes from the design or cell chemistry, something which drives to the software team, which may not be recorded into the requirement document, because the same requirement document will go to the software team as well. So it's all kind of file based, disconnected way. MBSE replaces all these with models. So instead of a document scattered across the team, we build the system model. So we use here, there are a lot of tools available. So we use here something called no magic, which is the SysML model. Entire our architecture is defined as a models. It has a requirement model, functional behavior model, and its interfaces and its constraints. By doing this, I can able to completely have that traceability. These requirements connects with this particular design. The same time, the requirements as a connected test cases for the verification and validation, and what are the interfacing component, so which will help us to identify early failures in the form of FMEA, correct? Design failure mode effect analysis. The same times that feeds into our manufacturing, so I can do early manufacturability, something called DFM, design for manufacturability study. So then that fits into the product failure mode effect analysis. That is mainly on the manufacturing side. What are the potential failures can cause? What is the mitigated needs and all those things? So everything I can able to see in terms of digital models and its traceability. So it is very much kind of helping us. So the system models becomes a single source of truth for mechanical, electrical, and software team, and verification validation. That is very important. Okay. So I think the big message here is, as a summary, I would say system thinking is a mindset. The MBSE is a methodology, brings that mindset into the practical approach. Okay. You guys are not overwhelmed with the message, correct? I'm keep on talking. I think it's good, correct, Manoj? Please stop me or raise your hands anywhere if you want to have any more questions or clarification. Okay. But definitely at the end of the session, I'm going to have the QA session. Bear with me because it's a lot more to digest, and I compressed these entire things into close to 20 to 22 slides to give more holistic context. Okay. So just now we have introduced the MBSE to all of you. Let's talk about what actually it enables. Definitely, it enables the innovation. The traditional development often follows a linear approach. We design, then do the prototype, and finally test. Then based on the test feedback, we correct and repeat. Definitely, it slows down the entire product life cycle process. And the most of the time, the problems we are finding out late in the game. After testing, there is issues. Then again, we'll come back to the drawing board. Okay. But this model-based systems engineering, what enables us is to simulate alternatives, and kind of definitely we can think about multiple alternatives. If you, for example, if you take performance or cost or sustainable, these three as a parameter, we can kind of do some sort of trade-offs. If I reduce here, but still I can achieve a little bit more here, something like that. I'll give you some example later, correct? And also we always by this MBSE approach, not just I feel this, not opinion based decision. We always make a data which will help us to make a better decision. That's what I'm trying to say here. So I'll give one example. Suppose we want to balance these three competing goals. What is that? We need to kind of on the acceleration and the range or the cost. So if you think about this, all handled by the different team. We have a dedicated team to focus on the range. We have a dedicated team focus on the acceleration, and definitely my finance PD works on the vehicle overall cost. Okay, so all these teams work in silos. Each team, they push their limits for their own optimization. Like performance team wants to have more power. The sustainability team wants the vehicle weight needs to be reduced drastically. The same time, the finance team want the lower cost. But if they don't have this holistic picture, definitely it's very, very difficult. But the model based engineering, because all those information is available and it's well connected, so I can just tuning this button here and there, I can simulate what exactly happens on each of this parameter. I can find some sweet spot which is best works, and if I compromise acceleration, still I'm able to achieve the sustainability. That means the vehicle weight will be reduced, and the same time I'm reducing the cost. I can give more range to the customer. So those kind of sweet spot I can able to simulate within this model based systems engineering environment. Okay, again the key takeaway here is, it is not just a documentation, it is a decision making tool which help us to kind of take some sort of action, and we can able to definitely innovate product more responsibly, and the same time sustainability as well. Okay. Okay. One of the most common question here is, do we have to use the same tool to achieve this MBSE? Correct? Most of the time, no, because every team has its own tool, and our main goal here is federate the information into the same form and shape as output. Whatever the outputs comes from the individual teams, like a mechanical engineer, electrical engineer, and software engineer and manufacturing engineer, they use their own tool, but those outputs connected through the shared model in terms of requirements and interfaces. Okay, so by that we can get this holistic view. So most of our CAD teams definitely uses their CAD modeling software, either ProE, CATIA, or NX, and the electrical and electronics teams use their specialized tool like OrCAD or some sort of specialized tool with respect to E. And the software team mostly use Jira or GitHub, or now lot of plenty of tools, but all of them something in the shape or form, it's connected through the system modeling tool as output to track this entire traceability. Okay, so what is the key takeaway here is, still they can work on their specialized tool, because we are not asking them to come into the one single source or one tool. It is mainly we are trying to federate those information to take a better decision. So it's mostly on not forcing in one tool, it's federating the information so we can connect them well, so we can take a better decision. Okay. And the next concept which we talk is about the system thinking approaches. Mainly, I'm going to introduce another very important concept in the systems engineering which we follow is shift left. So what exactly it means in our automotive or in the industry world is, traditionally all our validation and the testing happens late in the process. Once my design is completed and prototypes, in the prototypes, they do the verification and validation. So by that time, the fix is very, very expensive. So what shift left means is bringing the validation parts very earlier. So how? So instead of spending a single penny with respect to hardware, what we do is we use these models to do the feasibility in the concept stage itself, which is something called advanced engineering. So we do the engineering in advanced way with use of these system thinking and more MBSE tool sets, which will help us to do without kind of making any actual hardware to do the test. We do digitally using this kind of virtual simulation or virtual validation, etc., etc. And of course, we will validate, as I said, the entire requirements within this digital tool, so we can understand if, because each of these requirements is written by multiple different tech specialists specialized on those fields. Because how this requirement cycle will flow is we have the L0. Normally the term is L0, L1, L2, and L3. So like as a system requirement, subsystem requirements, and component requirements. The system requirements is very broader level, which is defined by marketing and few of of course, sometimes that is driven from the customers or the people like you expect something, so we will do some sort of market survey and capture this is the holistic vehicle as a system requirement that decomposes what goes to the software, what goes to the hardware, and what goes to the electrical architecture. Then that further decomposes to what is chassis. This exactly that entire decomposition happens. While writing this requirement, no one has this holistic view. Each requirements, it is more seamless. There are conflicts between those requirements, correct? So those kind of information we can able to identify very early in the game, so which will help us to kind of fix in the requirement stage itself. So we are not kind of catching those requirement conflicts in late in the game. So this is one of the kind of main advantage to shift left. Okay. And so now some of you might be wondering, that is sounds reasonably good, but do you think it is heavy, the process wise or our methodology or tools wise, it might be too heavy? Of course, kind of it is by looking into at first, looks like it's too much heavy. But we introduced the another concept, something called agile methodology. Traditionally, all the traditional approach is more on waterfall, it is more sequential, but we follow along with the systems thinking with more agile, which will help us to do file fast. That means instead of kind of filing in the late, we quickly put this, kind of first we'll define the targets and KPIs, and then we will build the architecture virtually. Sometimes we will not, because it's already created for one product, we can try to reuse the existing models, so that accelerates again, and we do the early validation within those models. Finally, kind of we can compare multiple variants, we can do the trade-offs. So if it's not working, we'll throw out and we started with the next iteration. So agile with system thinking is more kind of easy, and it pays off a lot for us and finding the problems very early. So that is the way the traditional companies takes 4 years to launch a product. Any new age startups, they can come the products very quickly, very faster because of this kind of methodologies and tool sets. So they are, even without spending any money with respect to the hardware build, the virtual validation, we used to call it the digital twin, is helping us a lot to do this early validation, finding the early problem, find early to correct early. Okay, so that is the main thing. Okay. Let's zoom in now on what system engineering really means into the practical. Okay, so these are the different components which I talked. We have requirements, mechanical, electrical, and so on and so forth. System model, it is not just a kind of diagram. It's mainly connects the actual entity to collaborate. For example, the requirements from the stakeholders and the same requirements, it feeds to the mechanical and electrical design that I can simulate with the software behavior and all of these entire things. Today, we have the digital model, something we used to call digital thread or digital twin with these MBSE tool sets. Okay. So the formula here is system thinking is not something, it's a mindset. The MBSE, it's a methodology, but puts together, it's definitely, kind of creates the collaborative backbone to interact all these different silos into a single source. So that's where the traceability is produced. Any point in time, any of my engineer goes and click a button, automatically button in the CAD. If I open one of my design component, if I can click and I want to see the navigation, automatically my system will show, hey, what is this connected requirement and what is this connected TFMEA and what is this connected test cases, which revision of the design is connected with which requirement. I have created the new revision. What revision it is, kind of what requirement is given that particular revision and connected change, and which has a lot more. So everything is digital thread, which is very much we are trying to connect as much as possible to provide the holistic visibility to take a better decision. So the systems engineering, this MBSE or systems thinking, whatever you call it, it is in the reality, it is something implemented through this MBSE methodology. That is the current trend. Okay, so let's talk about, I think pretty much all of you might have understood end-to-end process, correct? With respect to the entire product life cycle, any company, you have these product vision and target agreement. These are the different golden milestones in the product development. In most of the organization, including Lucid, we still treat development, it's like a relay race, correct? The requirement is once defined, we will throw it into the design. They will do the design, then we'll throw into the manufacturing. Then finally, it goes to the testing, then it goes to the customer, then service, correct? The problem is every of these hands off to kind of create some sort of silos as well as data loss. Okay, by doing this digital thread approach, what exactly it is helping us is everything is connected across these different gates, so we can kind of the benefit more here is in the concept stage itself, we can see how or we can involve our manufacturing team involved. We used to call it a set team. So every stages of these milestones, there is a set simultaneous engineering team which comprises of all of these people will be sitting and giving the sign off. It is not requirement engineers, then it goes to design. So each of these milestones, these set teams, that is another concept which we introduced here, something called simultaneous engineering team, which comprises of all of these people will be part of this each of every decision throughout the product life cycle. Okay, so even the set team is not just a team. Without the data, the team does not make any decision, correct? So these MBSE concepts will help them to give the data point to make those set teams on a better decision. Okay, so that is the main value. So what I'm saying here is the gates, all these gates should not be the walls, it should be the connected doors. That's what I'm trying to explain here, the concept on the MBSE side. So it is every gate, everyone will be informed and involved to take a better decision to move to the next stage. So when it comes to their work, they are very much aware what was that earlier as a team which we took the decision. So they know what is the deliverables. It will be smooth and quick, so they can move to the next stage. Okay. So this is a very complex V model with respect to EV engineering. We try to put it into the simplified way. If you see here, there are a lot of teams involved here, starting from the governance team, and we have MBSC, which is as we definitely kind of spoken a lot in the previous slides, and how the MBSC it connects with various teams and departments and deliverables and etc. etc. Maybe I'll just put it into the simple way. Definitely, this MPSC is very much important, more than any other industry, for electric vehicle engineering. Okay, because the EV is most interdisciplinary product in automotive world, which has hardware in terms of battery, motor, inverters, and definitely we have specialized EE architecture, which has complete harnesses and ECUs and sensors. And of course, everything is both controlled through the software in terms of controls, infotainments, and OTA updates. And definitely all those things together need to have some sort of simulation and validation through virtual twins. And there are a lot of validating environments. We do a lot of bench tests. And of course, there are still we work with a good amount of suppliers on their subsystems like seating. Today, in traditional cars, the seating has very mechanically adjusted. Today in EVs, we have, in the seat itself, we have close to 50 features. Like it should have the massage has 3 modes, and heated seat, ventilated seats with multiple 6-way, 8-way, 12-way adjustments, and etc. etc. The complexity. So everything needs to be connected with controls, electronics, softwares, wiring harness, and ECUs. And all this connects with our safety systems, like the airbags, because the seat also has airbag, and it's really complex. Okay, and finally, before selling this kind of beast to our customers, definitely we need to validate thoroughly. Each of these elements needs to work in picture perfect in the right place at the right time. Correct. So everything needs to be properly, thoroughly validated. We need to have some sort of multiple validation loops. So every time we cannot go back and build the entire vehicle and start validating it. We have to validate as much as possible, virtual iteration. Then we will do the prototype. Finally, that's what our EV's main goal is: how to reduce the cost. We do as much as possible virtual simulations using this kind of techniques, and we produce very less prototypes, so the cost is less, and directly we'll move to the production. So that is the way we can reduce our entire product development life cycle. So in a nutshell, as a summary to remember here is, EV is not just cars with the batteries. It is system of systems. Okay, and the system thinking is the only way to make this product as sustainable. Just take a water a little. Okay, we talk about end of the day, this is a business, correct? Now let's connect this entire concept to the business side, because the system thinking is not just for engineering hobby, correct? So we are not doing for hobby. It is definitely responding the business needs. So most of the time, executives or leaders often ask these 3 things for us, correct? Hey, have you captured all the requirements very clearly, correct? So how can we collaborate, kind of better with our internal as well as external suppliers? So most of the time, it is their classic question is, hey, how we can able to reduce the cost? The value engineering team is keep on bugging each and every team. Hey, this is your cost target. This is your cost target. Please try to reduce it as much as possible, because in the long run, most of the EVs today, whatever the product we deliver, it is not much profitable, because we need to have the volume. The same times, we need to always try to optimize as much as possible to reduce the cost, so we can reduce the cost of the vehicle, and overall that value needs to be cascaded to the market, so we can able to sell more costs. End of the day, it's all business, correct? So systems engineering and MBSE is directly address all those 3, correct? So we can able to capture our stakeholder needs, not in form of as a textual documentation. We capture everything in terms of models. Okay, the same times we have to collaborate with multiple people internal between the teams, and within the teams outside of the company. So it's all I have to collaborate. For example, today Lucid works with 3 vendors. For our recent rideshare project, we have to Uber is our end customer. We used to we are the integrator, and I have kind of getting from some technologies from Neuro. So all these 3 parties, I have to Uber defines the high level requirements, and as an integrator, I have to work with my other suppliers to get their components and integrate into vehicle and deliver it to the customer. So I need to handle this kind of people with it's email. It is not the option at all. So we have to have some sort of system which digitally help us to collaborate and interact with them. And finally, based on all their requirement is met, I have to produce the evidence. Hey, Uber, you asked, these are the high level requirements. I built the vehicle, I tested the vehicle. So this is my evidence for you, what we have done. So everything is achieved. The sign up is very much important. So we are not just taking a decision based on some sort of opinion or Word document or something. So we have to have some sort of connected logical system to produce those kind of results very efficiently and accurately. Okay. Definitely, the system engineering is not just a technical methodology or whatnot. It's definitely a business enabler. Okay. Okay, so I have to bridge this towards this decarbonization, correct? Sustainability. End of the day, how to reduce this carbon footprint across the multiple ways, correct? EV has taken a step forward because that is one of the key. So let's connect sustainability directly to our engineering, correct? The decarbonization is a journey, okay, to reduce the carbon emission, and it is not a step-by-step problem. It is a chain of stages. If you see the swim lane, so you have kind of authorities. So it is actually started around 2010. Then kind of every country, they had their target to reduce the carbon footprint by kind of switching to this new age hybrid or complete electrical mobility by 2035. Correct? For that, definitely the vehicles, specifically the automotive sector, is taken an early path to do some sort of research in terms of battery technologies and the engineering and mass production and sales and everything through this timeline. And of course, that leads into the kind of infrastructure challenges. So we need to have that kind of infrastructure in terms of charging stations and this, if we are trying to do as an alternative fuel like hydrogen, and all those infrastructure planning is very much needed. And it comes to more connected cars, which needs a lot of apps and kind of that apps comes with this security threat. So the cyber security rules and regulations and everything, correct? It's a journey. So we are kind of going step by step with a gradual transition. With respect to EV, definitely there are 5 stages. In the product development, we used to care about materials, which is lighter and greener materials to support this decarbonization as much as possible. And of course, the manufacturing, all our manufacturing is green field manufacturing. We started from the scratch. So it's not something we bought some existing manufacturing plant and build our product. So our manufacturing, advanced manufacturing plant 1 and 2, which is there in Arizona, as well as Kingdom of Saudi Arabia, both kind of we planned reducing waste as much as possible. We use a lot of renewable energy, and we control the emissions as drastically as possible in the plants as well. And of course, logistics is side also. We have done a lot of co-located logistics operations in our manufacturing. So it reduces shorter transport in terms of emission perspective. And of course, while using the vehicle for our customers, we had put a lot of effort to increase. One of the example is charging time, correct? So we reduced the charging time, so customer may not spend more time, so which some form of savings there. And of course, we give a lot of vehicle efficiency. So one of our main selling point, Lucid Air, is it is 512-mile run per charge. Okay, so I'm in San Francisco to Los Angeles, so I can do one stretch without stopping anywhere. So that is the kind of range with less battery and less power, and a smaller motor we could able to achieve with good aerodynamics, which I thought about, correct? And definitely after the fact, end of life, whatever the product which we made, it should be recyclable. So these are the key things, especially with respect to decarbonization in Lucid, we are taking care. And okay. So let's talk about kind of it's a 15 minute topic, but I due to the time constraint, I have kind of try to reduce it or simplify it as much as possible. So how do we make sustainable in the practical and engineering, correct? By linking directly into our system models is one of the things which we talk, and also the sustainability, definitely we don't treat as an afterthought. We treat is another requirement. Whenever we create any requirement or in the product development early stage, we'll keep sustainability is one of the key requirement, like other performance requirement or safety or cost. Okay, so for example, when we model a battery pack, is one of the example, is definitely we include the cell chemistry impact and manufacturing steps of the battery cells, as well as what is the thermal management, which will drastically adds a value in the battery pack. So that will in turn gives a longer range. Of course, how much kind of that entire pack is recyclable, and what are the potentials. The same way for motors as well, we consider the efficiency and the material which we source. Of course, kind of energy use across as a system, as a car. Okay, well, how much energy is consuming for overall end of the life cycle. So that's where the range, performance, and everything is matters. With a smaller battery pack, I will give one example. Okay, if I try to reduce 5 kg of weight in a vehicle, it seems very small, correct? So always my sustainability team is always fighting or giving the target to the engineers is as much as possible we have to reduce the weight. So, but over the lifetime of the car, definitely it reduces the energy consumption very significantly, and also the recycle is very much easy, and this small change definitely uh, helps us to do multiple sustainability events. Okay, so for the key takeaway here is sustainability is not just a checkbox for us; it is engineered in every decision throughout the systems thinking. Okay. Okay, I think we are kind of conclusion stage. I think I have covered a lot through this, kind of more than an hour session. And what we have done is, what does the sustainability means in terms of engineering, and it's about creating the system that last, adapt, and deliver the value in very responsible way. So, and something which we talked about, what is system thinking? Definitely, kind of. It's a mindset, correct? The system thinking is a mindset. It means looking beyond the silos, seeing the connections, and asking, if I change X, what is going to impact on Y and Z, etc., etc. And also we explored the model-based systems engineering. So that will turn the mindset into the practical way in our day-to-day practice. Definitely, it is replaces our entire documentations with integrated models. So the models, we capture the requirements, we do the behavior analysis, interfaces, we can clearly visually understand. And of course, by doing that, I can able to play around different Hello. 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 Can you guys hear me?
Yes, sir.
Hopefully you can hear me, correct? So audio is fine, correct? I was seeing some mute.
No, it is audible. You can continue.
So previously you can able to hear, correct? Whatever I was explaining to you guys, correct?
Yes, you are in conclusion part. Right, sir.
Yes, can you hear me?
Yeah. Please.
Hey Manoj, kind of throughout the session you had the audio, correct?
Yeah. We had idea. Is there any problem?
No. I
No,
thought
possible.
I was seeing in my kind of Zoom it was on mute. So I'm just wondered it is throughout the session slides you can able to hear me, correct? Whatever I explained you, correct?
Yeah. We have seen everything.
Okay. Thank you. This is my end of the session. I'm kind of glad to be part of this. You have any questions with respect to systems thinking or MBSC? I'm definitely here to answer you guys.
The participants, the forum is open to you. If you have any queries and questions regarding this session, you please figure out. You can switch on your mic and you can ask the questions if you have. Otherwise, you can share in the chat box also. Participants, any queries from your side? If not, we can close the session. No queries? Mr. Praveen, I hope the thing is very clear. The presentation is very clear, and definitely you have learned a lot regarding the EV, the uh, things what are all happening in the industry side, and other kind of stuffs we really learned. It's a very new kind of thing to us, and I thank you so much for spending your valuable time. Thus, I can understand that you are in your office. Am I right, Praveen?
Yeah. I mean, I came early today for this.
Yeah.
So it's 8:30.
For the sake of the presentation, you came early to the office, and but you have spent a lot. I can see your presentation. You have spent a lot of time to make it clear because a lot of things are happening inside the industry. I can understand when we are speaking personally, you discuss a lot regarding this, and I can understand you have made a clear presentation, so that the audience can easily understand the things which are all happening in the EV industry specifically in terms
Yes,
of
thank you,
engineering, in
Manoj.
terms of sustainability, and in terms of all other kind of managerial issues that are all happening inside the industry. Thank you so much, Mr. Praveen. On behalf of the Department of Mechanical Engineering, Adishanga Deemed University, once again, we thank you for your acceptance and spending your valuable time in between your busy schedule for the sake of our audience, for our participants. Thank you so much.
No worries. Thank you, Manoj. Thank you, all of you, for that valuable time. It's 1.5 hours really, we need to value. So I hope I have, kind of took all of your time in a meaningful way, and I given some insights based on my experience. Thank you.
Yeah, basically, most of us are belonging to academics, but when we have people like you on board, then definitely we are having a different kind of perspective and view regarding what is going on in the industry in terms of the emerging areas like in the EV industries and all. Yeah, once again, thank you for your kind presence over here.
Thank you, Manoj. Thank you. Thank you all.
Thank you. Dear participants, the feedback link for session 4 is shared in the, wrongly shared. Feedback link is shared in the group. Once again, I will share. Please fill your feedback form before you are leaving from the Zoom. Yeah. So that's all. Thank you, everyone, for your patience listening. Hope both the sessions today, we have a lot of takeaways from both two sessions, which have been handled by Dr. P.P. Chandramohan as well as Mr. Praveen Kumar Pugaledi. And tomorrow we have another 2 sessions like this. We will start by 6 o'clock sharply. And I request everyone to join at least 5 minutes before the session so that without any delay, you can start the session sharply by 6 o'clock. And tomorrow we have 2 more guests. One is from an academics who is having much experience in renewable energy. He's Dr. T.V. Arjunan sir from Guru Gasidas University, Chhattisgarh. And another one is from industry. Thank you, everyone. Kindly fill your feedback form before you are leaving the meet. And if you have any issues, then and there, please let me know. Let us know through our personal chat so that we will try to rectify those things.
Sir, excuse me, sir.
Sir, please.
Sir, after filling the feedback, total points 0 by 0 it's showing, sir. By selecting 5, 1, 2, 3, 4, 5, all are selecting, sir. It is okay.
Sir, actually, this feedback is for the sake of consolidating the attendance.
Okay, sir.
Actually, it's basically a rating kind of feedback. If you give 5, it means 5 star. So all the 5 stars will be blocked. If you give 2 stars will be shown. It's a kind of star ratings.
Thank you, sir.
And at the end of the program, you have to give another feedback. That is the main feedback through the ATAL portal through your login. So that is one the major main feedback that will be taken by the concerned authorities. So these feedbacks are for the sake of getting your feedback regarding each and every session. That is for our own sake and for consolidating the attendance.
Thank you, sir. Thank you. Thank you.
Any other queries from the participants, please let us know.
Hello.
Any other difficulties from participants, please, sir. Manisegaran, sir.
Yeah. Yesterday, I forgot to fill up that feedback form. Can you send? Otherwise, no need.
Yeah, no issues, sir. I think I already shared with you morning message, I think so.
Yeah. I sent mail also.
Yeah. You see the mail and I also saw your message. I shared with you, sir. Please check, otherwise you put another message, we will share you, no problem.
Thank you.
See, if you have any issues, queries regarding the conduct of the program or organization of the program, please let us know immediately so that we will try to solve at the earliest possible. The objective of this program is to share our knowledge, to share the knowledge of the resource persons to each one of you and with us also. So that is why the major objective. Okay. So in that, if you have any other issues or queries, please let us know in the group. No issue.
Okay, sir. Thank you.
Yes, we have shared the attendance Whatever you have taken the attendance from our side, we have shared in the group. If you have any issues in that too, please let us know. We will solve it, no problem. So it is the draft attendance what we have prepared. Okay, after getting verified with each and every one of you, we will post it in the ATAL group, ATAL post portal. Because once we post in the portal, then we cannot change it. So before that, if you have any queries, please let us know. By tomorrow, you will start posting the past attendance in the portal. So before that, if you have any other queries, please let us know so that we'll solve on hand. If you don't have any other questions, we can wind up the session.
Thank you.
Yeah, thank you everyone once again, and we will meet again tomorrow evening by 6 o'clock. Thank you, everyone.
Yeah,